Okay, Eric. So for calculating antiderivatives and integrals, just think first of all about the derivative. The antiderivative is essentially just going backwards. So I got some notes here that I'll just post so you can pause the video and read my notes if you need to. I guess I could also take a picture of these and send them to you. Just take a look at those. Maybe they'll help, maybe they won't. I'm not really sure. If you look here at the ladder that I have going, you could think about it as if you just have a general function and you have a ladder, and you can go up the ladder and down the ladder. And as I have a function, I can differentiate it multiple times. And you can call the function whatever you want. And so you can take the derivative of it, you can take the derivative of that to get the second derivative of your first given function. Well, antiderivatives are just going back up the ladder. So if I give you, let's say I give you a formula for the acceleration of a particle. You know, you've dealt with that with throwing balls and stuff up into the air. So if I give you a formula and I tell you this is the formula that describes the acceleration of a particle, and I ask you to give me the formula that describes the position of it, what you would do is you would take that acceleration formula and you would anti-differentiate it. And that would get you back up the ladder 1. And if the derivative of velocity is acceleration, then the antiderivative of acceleration is velocity. You got to think about it as that step by step on a ladder. So you anti-differentiate acceleration to get to velocity. You anti-differentiate velocity to get to position. So that's the first thing. It looks like that. And the antiderivative formula for just simple variables, when you had x squared times x over 2 squared, square root, all that stuff, when you had all that stuff multiplied together with derivatives, there were some formulas, like the product rule and the chain rule and the quotient rule. There's stuff like that when you anti-differentiate, and you'll get there soon, I believe, when you start talking about substitution and integration by parts, but it's down the road. So the is this first, and I bet you've seen this, is that the antiderivative of x to the n is right here. It's x to the n plus 1, that's a power, all over n plus 1. Right here, I've written up a little thing about y. So you can see is if I just say some function that I called h of x equals x to the n, just any power. The antiderivative, which you've probably seen notated as with a capital letter, is going to be x to the n plus 1 over n plus 1. And the reason why is in order for anti-differentiation to be like the reverse of differentiation, you got to make sure that everything will work out when you do it. So if I give you capital H of x and I just say, hey, it's x to the n plus 1 over n plus 1. Let's say x to the 4th over 4 or something like that. And I ask you what the derivative is. Well, to take the derivative of an antiderivative, you'd bring down that exponent. Where did I do that? Over in here. It's kind of backwards on my screen. You bring down that exponent, and you subtract 1 up top, and then you're left with n plus 1 times x raised to the power of n plus 1 minus 1, because that was our derivative formula, all over n plus 1. Well, those n plus 1s will cancel out, and then you're left with x to the n, which is what lowercase h of x was to begin with. So that shows us that the antiderivative formula works. It does get more complicated eventually. Hopefully you're not there just yet, so you can get a grasp on this. So that's the basic differentiation, anti-differentiation. You're just kind of going up and down a ladder. There's one important thing, though, to remember. As you move down the ladder and you differentiate a function, it becomes more simple, right? Because, if you had just x, and then you take the derivative, then you get a constant, which would be 1. Or if you had 4x, the derivative is 4. And when you differentiate that, you get 0. Well, when we go back up the ladder, we got to make sure we account for those constants. So what we do, I didn't write it in there, so I'll do that right now, is you have to add this constant factor. The reason for that is that if I take the derivative of an antiderivative, that c would go away. So over here, you could think about it that that lowercase h of x, think of that as x to the n plus 0. Then, down here, my capitalized h, my antiderivative, is x to the n plus 1 plus c. Let's see, how do I explain that? Here's why. Remember, derivatives are just the slopes of tangent lines. Slopes of tangent lines don't matter they're not dependent on like where the graph is. So if I have a graph, let's say it looks like x squared. If I have one that's like x squared plus 3 and one that's just x squared, I didn't label much, but like here's x squared plus 3, ish. The slope of the tangent line at x equals, let's say, 2, those slopes are the same. And it doesn't matter that in one graph the curve is shifted up on the y-axis or not. The slope of the tangent line at that point is the same. So that's why that constant has to be there when you antidifferentiate, because when you take the derivative of an antiderivative, that constant goes away. But if I said find the antiderivative of x, antiderivative of x is x squared over 2. X to the first, do our formula, x to the n plus 1 over n plus 1 would be x to 2 over 2. Let me think of a better one. Let me do find the antiderivative of 1/2 x. So if I give you that, like, I'm just going to call f of x is 1/2 x, just right there, very simple. The antiderivative, I'll use that capital F, which I'm sure is what your book uses, is 1/2 x squared. That first function, make it 2x. I apologize. Make that original function 2x. There it is. My antiderivative is going to be x squared over 2. So 2x squared over 2 is just x squared. But the antiderivative needs that constant factor, plus c. Again, the reason is that original function, x squared, which I have up here, that could be x squared, or that could be, 2x. The original function is 2x, not x squared. The original function is 2x. That could be 2x plus 6, for all we know. Because the derivative of the slope of the tangent line doesn't matter if the curve is here, or up, or in the middle, because the slope at a certain x value doesn't change. So when you antidifferentiate, you need that c. Now, if I was going to antidifferentiate the antiderivative, then I would need to do, I'll write it down quick. I antidifferentiate that first piece. So there's x cubed over 3. That's the antiderivative of x squared. The antiderivative of c is cx, because the derivative of cx is c. And then I would need a second constant. I just did a k. Just another term for constant. So that's to deal with antiderivatives. Now, integrals. Integrals are a way of finding the area underneath a curve by kind of breaking it up into an infinite number of little boxes. So I don't know if you've seen this or not, but finding the area of boxes and shapes with straight lines is really easy. We know how to do that. But when we have a curve, we've developed a way to do that using limits. So if I give a curve, between, I'm going to call these 2 points A and B. So I'll show you this in a second. Here's a curve, and there's a section of it between A and B. I can estimate the area underneath that curve by drawing little boxes. And the more boxes I draw, there's some boxes. The more boxes I draw, like the shorter, the smaller the width is, the more accurate it's going to be. But right now, I've got some pieces like right here and there, these little areas that they wouldn't be accounted for. And so what an integral does is it takes a limit of these boxes essentially and makes it so that the width is really, really small, and then it essentially lets us calculate the area underneath curved lines. The way to do that is to, I think I actually wrote that on that first page. You find out, you look at your integral, and it's got some pieces. There should be like an S sign with two numbers. There should be, in here you could call that a function or addition of two functions. This could be f of x and g of x, or this whole thing could just be h of x, whatever you want to do. And then this dx. That dx is important for integrals, and it's hard to explain right now, but I can show you that after break when we meet up. But what you do is you take the antiderivative of the inner part, the part between the s and the dx. Take the antiderivative of that. So the antiderivative is over here. It's x to the third over 3 plus x squared over 2. That's exactly what I showed you all up here. And what you do is you evaluate that antiderivative at these 2 points that they give you, at 1 and at 4, which is right here. You can see where that came from. I didn't write down that number. I should have done that. It's going to be some kind of fraction. And the difference between those two, sorry for moving around so much, here's the antiderivative evaluated at 4. Here's the antiderivative evaluated at 1. The difference of those two things, of the antiderivatives, evaluate those 2 points, that's the area underneath the curve. There's some math behind that. There's this thing called a limit of a Riemann sum. If you'd like, email me and I can upload a video explaining that. There's some good stuff on YouTube about Riemann sums already. But that's what it allows us to do, is you look at a curve and you say, I want to know what the area is under point A and point B. And so you have this interval between A and B. So you take the antiderivative of the curve, you take the antiderivative evaluated at B, you take the antiderivative evaluated at A, and you find the difference between the two. The difference meaning subtraction. You subtract one from the other. And what you get is that's what's left. That is the area underneath that curve. I hope that helped. If it didn't, I can try again. If you have more questions, shoot me an email, and I'll be checking that. Hopefully this helps you again, and hope you have a good break. All right, I'll see you later.